Hi, and welcome to this instalment of the SLAC Public Lecture Series. I'm Dr. Nick Edwards, and I'm a Research Associate at SLAC National Accelerator Laboratory. For this lecture, I'm going to tell you about how my colleagues and I have used the intense X-rays generated by a particle accelerator, SLAC's Stanford Synchrotron radiation light source, to study fossils and discover the colours of ancient creatures. Now, I've already mentioned quite a few big words there. Don't worry, I will go through everything you need to know. If you still have questions at the end of this, or maybe want to know more about a particular topic I discuss, join us for the live Q&A Zoom session on the 2nd of June at 7:30 Pacific Time. The details are on the SLAC Public Lecture website. We're going to be joined by Uwe Bergman, who is our group's resident physicist at SLAC, Roy Wegelius, our lead geochemist from the University of Manchester in the UK, and Jennifer O'Neill, the lead paleontologist at the Children's Museum of Indianapolis. We also do research other than discovering the colour of fossil creatures, so if you'd like to hear more about that, then zoom in. If you're watching this after June 2nd, don't worry, the Q&A session will be posted online and maybe your question was covered. So, what to expect from this lecture? Ultimately, I'm going to talk about how, over the last 13 years or so, my colleagues and I have essentially tried to understand what fossils are made of. So, it's a commonly held view that fossils are just dusty lumps of rock, like this ammonite, and skeletons in museums, that essentially just tell us about the shape of extinct organisms. Now, there is a lot a paleontologist can decipher from these fossils. For example, they can give us ideas about how an animal moved by seeing how the bones fit together. And we can interpret evolutionary relationships by tracking the changes in the shapes of bones and other tissues through time. And we can interpret things pretty obviously like diet from things like the shape of teeth. But ultimately, all matter, be it a human, a cat, or something non-biological like rocks or metal, are made up of atoms of elements, arranged in an almost infinite number of ways. How different atoms combine together into different materials defines their properties and how they behave. Now, a biological system, like a human, is just a big bag of wet chemistry, and you've probably heard us being described as being carbon-based. That's because we're mostly made up of the element carbon. You're also probably familiar with iron that's in your blood or calcium in your bones, but you may not realize that we also have a lot of other chemical elements like copper, zinc, and manganese, and many more that are integral to many of the molecules that make you, you. Molecules like those that make your hair, eyes, or skin a certain color. It is this chemistry that I and my colleagues are interested in because if we can identify elements in specific parts of a fossil that came from the once living organisms, we may be able to gain new insight into how this animal actually functioned at a biochemical level. Now, the holy grail of this biochemistry is DNA, the blueprint for an organism. Unfortunately, DNA degrades very rapidly once an organism dies, and we're not going to be talking about it here. We're going to be talking about trying to identify elements in fossils that may indicate the presence of certain biochemical processes, and in this lecture we're going to focus on those elements associated with colour. Now, you may not realise that until recently we didn't actually know the colour of extinct life forms were, despite what you may have seen in movies or on TV. There is very little direct scientific evidence for colour in the fossil record. This, for example, is technically as valid as any other colour reconstruction. And we're interested because colour is very important to life in general and defines many of the ways that an animal behaves, such as being camouflaged or being brightly coloured to attract a mate. Pretty important behavioural characteristics, so you can understand how paleontologists would be interested in these details. But before we go into that, for the first part of this lecture, I'm going to talk about how we can uncover this information, and in this case the way we obtain the data we need is just as cool as the data itself, and I think it is important that we take some time to cover that subject. So first, a little bit about me. How does a little boy who liked dinosaurs from England end up working at a particle accelerator in California? Well, as you can see, I like dinosaurs ever since I was a little kid, and I always wanted to be a paleontologist. So I had lots of other interests at school, and as I grew up, my interest for dinosaurs and paleontology never really went away. So I decided to pursue that as a career. Now, there aren't really any degrees in paleontology exactly, but there are degrees in geology where you can specialize in paleontology, so that's what I did. I went to Royal Holloway University of London, not too far outside of London, and I graduated there in 2006. And then I decided I still like rocks and fossils, so I decided to go off and do a PhD, and luckily I was taken on to do a PhD in paleontology at the University of Manchester, which I started in 2007. And it was in the winter of 2007 that I first came across SLAC, a synchrotron, and the joy of X-rays. So we were invited by some colleagues of my PhD advisors to go visit them, seeing what they were doing some cool things with fossils at the synchrotron. And we were hooked immediately. The data that they were collecting looked amazing. We could really see some awesome potential for what the data was telling us about these fossils. And it was just super cool. It's a big science machine, big facility, really cool, big science. And so what they were actually doing was using a technique developed by a SLAC scientist called Uwe Bergman, who is joining us for the Q&A, where he had developed a rapid X-ray fluorescence imaging technique. Now, I'll get onto X-ray fluorescence imaging later, so don't worry about it. But basically, it's the ability to image the chemistry of a large object. By large, I mean bigger than like a 1 square centimeter or half an inch or something like that, whatever the conversion is, but a centimeter in real units. And what he did was look at some ancient manuscripts that revealed hidden writings underneath by being able to look at the chemistry below images covered over the top. And in this case, this was the Archimedes palimpsest. We don't have time to talk about this, but this kind of gives a general idea. And so those colleagues who invited us over had heard about Uwe Bergman's work looking at ancient manuscripts and thought, hey, this would be really cool with fossils. And then we came along as well. And so a bit of serendipity there. And yeah, kind of a bit stumbled on it by chance. But anyway, super cool. And we realized what the potential of this could be. I ended up finishing my PhD at Manchester in 2012. And through some of the results that we gained during those years while I was doing my PhD and as a research group in general, I'll talk about one of those papers later, but based on the success of that research, we got a grant to fund me as a postdoctoral research associate at Manchester, and I stayed at Manchester for another 4 years, continuing this work on using the synchrotron to study fossils and investigate colour. And then finally, after 4 years of the postdoc, an opportunity came up for me to move to California and join SLAC to work on the X-ray fluorescence imaging beamlines. And this was a dream come true because I always, this was the most, again, the bit that I enjoyed most about coming to the synchrotron was doing the experiments, and all the experience I'd gained over there kind of helped lay the foundation for what would become a career in synchrotron sciences. But before we start talking about specific fossils and their colour, I think it's really beneficial that we first cover how we actually collect the data using X-rays, specifically those produced by a synchrotron. And because the way we collect the data is just as cool as the data itself. So first, what are X-rays? X-rays are electromagnetic radiation, just like visible light, radio waves, and microwaves, among others you may have heard of. And all of this radiation travels as waves. Now, the electromagnetic spectrum is the range of frequencies and their respective wavelengths and photon energies. Now, wavelengths can range from thousands of kilometers all the way down to the nucleus of an atom. Now, the electromagnetic waves in each of these bands have different characteristics, such as how they interact with matter and their practical applications. Now, we want to use X-rays because they have high enough energy to ionize atoms, and I'll get into that when we start to talk about X-ray fluorescence in a little bit. But you'll be familiar with hospital X-rays, and that's because they have high enough energy to pass through fleshy bits but not bone, which is why we see a contrast on an X-ray film. But we need to generate these X-rays. And we need to generate lots of X-rays, and we need to generate X-rays in a very controlled way. so we can manipulate them and make them do what we want. And the way we do that is to use a synchrotron. Now, this is where really modern day physics meets ancient world fossils. Now, a synchrotron is a particle accelerator, and SSRL was one of the first synchrotrons. A lot of the research we do, we have also done at Diamond Lightsource in the UK, but basically a particle accelerator accelerates particles to near the speed of light using huge electromagnets. And that's an insane speed. That's about as fast as anything can go, as far as we understand it. Here we are inside the ring at SSRL, and you get an idea to the sort of scale of the engineering there involved in a particle accelerator. So the synchrotron was originally designed as a particle smasher, that is, sending particles in opposite directions through those electromagnets and smashing them into each other in order to study subatomic particles. But when these particles were accelerated at such insane speeds in a circular path, it was found that there was huge amounts of radiation being emitted out the side. And this was kind of a pain because we didn't want this radiation and it had to be shielded against. And that kind of was it for a little while, but then some clever people realized that this radiation could be very useful for performing a wide range of experiments. And so some clever people realized that if you could punch a hole in the side of the synchrotron and let some of this radiation out and then control it with different optics and different mechanical components, you could actually channel it and control it to do the things we want. And this is what's called a beamline. And a synchrotron now, and lots of synchrotrons being built today, are pretty much dedicated to generating synchrotron radiation as well as doing some particle smashing work. Now, there are many of these beamlines around a synchrotron. And SSRL has over 20 of these beamlines, with many substations in there as well. And research using the synchrotron SSRL covers a wide range of disciplines, such as the energy sciences, looking at battery technology, biomedical science, environmental science, and the one little bit that we do down here is our X-ray fluorescence imaging of things like fossils and ancient artifacts. Here we are inside SSRL itself, and here we are inside some of the experimental hutches where the X-rays come out. And so this is one of the X-ray fluorescence imaging stations where we try to understand the chemistry of ancient artifacts. So I've mentioned there X-rays and X-ray fluorescence imaging. So exactly what is X-ray fluorescence imaging? Now, I mentioned the ionization of atoms earlier when we talked about the electromagnetic spectrum and X-rays, and I'm going to go into that now. So, without getting into too much detail, light behaves both as a wave and a particle, and that particle is called a photon, i.e. 1 unit of light. And that's what we've got here represented in this little red dot, and represents one X-ray particle coming out of the synchrotron. And now we have here kind of like our stylized cartoon atom, which you may or may not be familiar with. But an atom, just to recap, is the building blocks of all matter, and each atom is an element, essentially. But the difference between the elements is their atomic configuration, actually. So an atom consists of protons and neutrons in its nucleus, and electrons orbiting around the outside. Now, it's actually kind of like a little cloud of electrons, but this is the best way to represent it in two-dimensional space. And the different configuration and number of protons, neutrons, and electrons determines what an element is. So iron has different protons, neutrons, and electrons to calcium, for example, and we'll show how that's useful in a second. But what we're going to do is ionize this atom. We're going to bother it. We're going to make it unstable using the X-rays from the synchrotron. So, this is really useful process because we use this to be able to identify elements. And so here comes our single X-ray photon, of which there are millions and billions coming out at any time, but this is just one representing one of them. It comes in, and it's high enough energy to knock an electron out of inner shell of the atom. This in itself is called the photoelectric effect. And as I say, now that state here is the atom being ionized. Now the atom wants to restabilize itself, and it does that by filling that hole we just created with an electron from one of the higher orbitals, like so. What's really cool about this is that change in electron falling from one orbital to another generates a brand new X-ray, which we call the fluorescent X-ray. Now what's really interesting about that is that X-ray has a wavelength, or a photon energy, that is characteristic to the atom that it came from. And we detect these X-rays, and by able to detect the wavelength or the energy of this X-ray, that means we're able to identify the atom that X-ray came from. Now when we're bombarding our sample with lots of X-rays from the synchrotron, we're exciting lots of different atoms at the same time. So we get lots of different fluorescent X-rays coming out of our sample of different wavelengths and energies. So how can we differentiate between them? So on the right here is what we typically get out of a synchrotron, called an X-ray fluorescence spectrum. That's when we just have our X-ray detector pointing at our sample while being bombarded by X-rays, and it's able to detect the different energy of those different X-ray photons and separate them out so that we can see them in this spectrum. And what we have here is the photon energy across the bottom and how many the X-ray detector has detected up the vertical side there. And so what we get is wiggly lines like this that show us how much of each X-ray we've detected. And so, for example, we have in this spectrum, we have lots of photons that have an energy of about 3,700 electron volts. And that is the energy of photons emitting from calcium atoms. And at 6,400 eV roughly, we have lots of photons coming from iron atoms, among lots of other different elements there. Now, as I said, lots of different X-rays of different wavelengths and energies are being emitted from our sample while we're hitting it with synchrotron X-rays. And so, this is represented here by this kind of a bit more simplified line diagram of the electron orbitals that I talked about, where one falls from a higher one to a lower one. Now we label these as these letters here, so K shell, L shell, M shell, N shell. And it's actually the transition between these different shells that generates different energies of photons coming out. So in this spectrum here, we're looking mostly at what we are calling K alpha and K beta, and simply that represents electrons that are falling from the L lines down to the K line here. That's the K alpha. That's one of the most dominant peaks we usually see in an X-ray fluorescence spectrum. The next one we commonly get is what's called a K beta, and that falls from a M line down to the K line, and that's why we call them K shells, because these fall to the K shell. There's also lots of other lines that we're not seeing in this spectrum, but a lot of research is done on as well. Excuse me, kitty, I need to show that diagram. Which is an M electron shell, an M shell electron falling to L shell. So those are called L lines, and then finally N to M. So hopefully that's a good, you can understand the significance and importance of that sort of atomic process going on in our samples and how we can use that to identify elements. Now that's great, we can put the synchrotron beam on our sample, and we essentially get an inventory of what elements are present. That's great and can be done in lots of other different types of instruments as well. But what would be really cool, and what's really interesting for us, is whether we can we really want to know what our elemental inventory is for different parts of our sample, not just under one particular spot. Now we could just drive around landing on different spots and collecting a spectrum like this, but that's not very useful and is actually could be quite time consuming. So what has been developed and is pretty common for different techniques, but I'll get into why the synchrotron is particularly good at this in a second, is X-ray fluorescence imaging. Now all that is that we have the same synchrotron beam, the same process is happening here. But what we do instead is we move the sample backwards and forwards in front of the beam. So here's a little cartoony animation of representing our X-ray beam coming from the synchrotron and our fluorescence X-rays coming out into a detector. And we're moving our sample backwards and forwards, and if we time our stage movement and our computer data collection properly, we're able to build up a chemical image pixel by pixel, line by line, and then we're able to see essentially a picture of where the different elements are. Here is the same, here is a representation of a real-world version of the animation here. So here we see a fossil going backwards and forwards. Now you can't see the X-ray beam, it's not like cool lasers or anything, but there is an X-ray beam coming through here. And here is our X-ray detector, and here is our fossil moving backwards and forwards. And as it moves backwards and forwards, we start to see the data come through live, line by line. So why use a synchrotron? Well, a synchrotron has many really awesome advantages compared to other techniques which can also generate X-ray images with this kind of process. The first thing is that the synchrotron generates lots of X-rays, much more X-rays than other instruments generate in their beams to excite their atoms. And that makes us much more sensitive to elements that are in lower concentrations. Now that's really important to us in looking at biological systems, because often elements are in very tiny quantities, but significant quantities. And quite simply, the more input there is, the more output there is. So statistically, we're much more likely to hit an atom that is in low concentrations with a lot of X-rays than we are with only a few X-rays. And the other advantage of having lots of X-rays means we don't have to sit on one spot for a long time to get a good signal. So we can scan faster, which means we can scan bigger things in a shorter amount of time. And that's really good for fossils in particular. Another good thing for things like cultural and natural heritage artifacts, such as fossils, is the fact that we can actually work in what's called ambient conditions. That is, we can essentially work in room temperature and normal atmospheric pressures, unlike other techniques like scanning electron microscopes, which require a vacuum chamber. And that's very important because a lot of paleontologists don't want us smashing up their samples into small bits in order to go do a bit of chemical analysis. Some fossils are extremely rare and precious, or sometimes there's even only one of them. So in order to do chemical analysis on a lot of fossils, you just couldn't do it. It wouldn't be allowed. So being able to put in a fossil untouched and unmolested into the X-ray beam, very useful. And it's also and because of that, it's also very flexible in sample size and shape. Fossils don't conform to nice, perfect samples that a lot of techniques require. So we can put in a big, lumpy piece of rock with a fossil in it, and the synchrotron handles it just fine. And finally, the final important thing is that essentially this technique is non-destructive. Unlike other techniques, as I said, where you have to smash things to pieces and coat them in things in order to look at them, the synchrotron doesn't require that. We put the sample in, we scan it, we take it out, and it looks just like it did before we did the analysis. And a lot of other analytical techniques actually destroy the sample during the analysis, so it's gone forever. So a lot of really good advantages there to using the synchrotron. Now, I'm not going to delve into this part too quickly, but it is really important because actually the way that we're able to manipulate X-rays at synchrotron beamlines means we can do perform an analysis called X-ray absorption. Now, I'm not going to get into much detail here because there's no time, but essentially what we do is we put our beam on our sample and we essentially generate a wiggly line, or called as X-ray absorption spectrum. Now, don't worry or start getting too overwhelmed by this. But the main take-home point from this is that the shape of these wiggly lines helps us identify the chemistry around an atom that we're interested in. So, for example, you may not know or may not realize that each element, depending on how it's bound in terms of its arrangement of atoms to other elements, generates different compounds. And a really good example is iron. So you have iron metal, Fe, but we're probably all familiar with the fact that iron rusts. And what is rust? Rust is iron with oxygens around it. And here is an X-ray absorption spectrum of iron rust on the left. And when we collect an X-ray absorption spectrum, the spectrum has a very specifically shaped wiggly line. Now, another type of iron is pyrite, or fool's gold. And that's iron, an iron atom surrounded by a couple of sulfurs. Same element, very different properties and characteristics. One is rusty brown, and we see it all the time. Pyrite almost looks like a gold color. And as you can see, the wiggly line here is very different to the rust. So X-ray absorption is extremely useful, and you'll hopefully see why that's significant when we look at fossils and looking at the elements that we're interested in. Because some elements are inorganic, some are organic and come from different places. They're surrounded by different elements. And so when we're doing our chemical imaging of our fossils, we want to know, are those elements organic or inorganic? What are they? Just knowing that it's copper or iron or nickel or whatever isn't enough. We need to know what's surrounding them. What compound is it, essentially? And that's important because we need to try and say with a reasonable degree of certainty whether the elements that we're seeing in our fossils have come from the external environment, which is likely after tens of hundreds of millions of years, or has it come from the organism itself? And hopefully we'll be able to tell the difference between the two by being able to perform this experiment and see their different atomic arrangements. So, not too much detail hopefully, but important nonetheless that we do cover the basics there. Now on to some data. Thanks for hopefully you've stuck with us for this long, and now we're actually getting to looking at some fossils. Okay, so we're done. We're done with the background stuff. Synchrotrons, X-rays, X-ray fluorescence imaging. Hopefully that was interesting enough and you're still here. But now we're here. We're going to see how the synchrotron has generated some really cool data. And we're actually going to go through a little bit of a chronological narrative here about how the research developed over the years of using the synchrotron, because we kind of didn't know what the synchrotron would tell us in the early days. We kind of started with the advantages I mentioned earlier, that we could look at fossils that couldn't have chemical analysis done before. And so we put in lots of cool fossils and kind of followed the data. We just wanted to see what the data showed. We really had no idea what we were going to find. And one of the actual driving thoughts that we had that the synchrotron could tell us was that we might be able to find things that we dubbed chemical ghosts. What do I mean by that? Well, I mean, is there hidden chemistry in the fossils that we can't see with the naked eye that might tell us something about the original animal that we didn't know before? For example, is there remnant chemistry of soft tissues which we can't see anymore with the naked eye, such as feathers, skin, fur, things like that? And long story short, the answer is yes. And one of our first discoveries using synchrotron X-ray data did exactly that. And even better, we did on one of the coolest, most well-known and important fossils ever discovered. This is Archaeopteryx. Archaeopteryx, you may or may not know, has been dubbed one of the world's first missing links between dinosaurs and birds. Now, things have changed a little bit in the last few years about evolutionary ideas between dinosaurs and birds, but really important scientifically and culturally. Scientifically, because, for all intents and purposes, Archaeopteryx looks like a dinosaur. A little dinosaur running around a lagoon area in Germany 150 million years ago in the Jurassic period. If you were to just look at its skeleton, it looks like a little dinosaur about the size of a chicken, as I said. It has teeth in its mouth, claws on its hands, and a long bony tail. So, as I said, that's a dinosaur by all intents and purposes. And actually, if you put this skeleton of Archaeopteryx next to another species of dinosaur called Compsognathus, you'd better be able to tell the difference. So what is the difference? Well, the stunning discovery when these first specimens were discovered back in the 1800s was feather impressions surrounding the animal, surrounding and attached to the skeleton. Now, it was a bit hard to see in that optical image, but essentially what you could see is things that looked like feathers, as though they'd been squished into the rock, but now the soft tissues of the feathers aren't there anymore. They're just gone away. It's literally like somebody pressed a feather into some clay and took it away. Now, this was a revelation because when these were first discovered, there was no indication or any idea that birds and dinosaurs might be related. And from the cultural point of view I mentioned, this is around the time when Darwin had published his first edition on the origin of species, where he suggested that species transition from one species into another. But one of the main criticisms of his work was that if this process happened, the process of evolution, we should see these transitional species in the fossil record. And up to that point, nobody had discovered any. And not long after his first edition, one of the first nearly complete Archaeopteryx specimens was found, showing exactly this: the two seemingly disparate features of a dinosaur skeleton, but feathers, which is the definition of a bird, attached to one another. So, really important from a cultural and scientific and paleontological view right there. And there are only actually, I believe, 14 of these in the world. This sample is number 12. Anyway, so this is actually number 12, and we actually studied the first one as well, called the holotype, which I'll get to later, and also another one, early one as well. And so this specimen, as you can imagine, has been extremely well studied. Paleontologists did what they normally do and looked at the shape of the bones and the feathers and tried to make evolutionary interpretations from looking at it under visible light, and sometimes some people looked at ultraviolet and other wavelengths too. But nobody had looked at the chemistry of this, and to all intents and purposes, people had just said, well, these feathers are simply impressions, there's nothing left there. That's all we can tell, is we can look at the impressions in the rock, and that's all we can tell. Now, we thought this was a prime example for the synchrotron. It's rare, there's only 12 or 14, there's only 14 of them, and there's potentially some chemistry there because we know that there's some indication of soft tissues. Plus, iconic specimen, really of wide interest. And the results didn't disappoint. Here is the key image from that work, which is the element phosphorus. Now, phosphorus is, as you may know, is part of your bones. Bones are calcium phosphate, mostly. And that means they're mostly made up of calcium and phosphorus. So it's no surprise to see that phosphorus is highly concentrated here in lighter white colours compared to less in the dark in the bones. But what was a really nice surprise was that we can actually see the central shafts of the feathers in phosphorus. And we can see them here and here. I'll zoom in a second, but this is the key to doing this large X-ray fluorescence imaging, because the sensitivity, and also a testament to the sensitivity of the synchrotron, because these are extremely faint signals that we're looking at here. And these are signals that we can only really tell are there because we see them and interpret them with our own eyes as following structures we see in the visible light. Other techniques, if we'd had to chip a bit off or put them in another X-ray source which could only scan a centimetre at a time, we'd have had to be very select about where we picked. And we may have missed this feature completely, but being able to scan the whole thing means we're able to see correlations between the feathers and the chemistry. And this was a really big result. And what's more, phosphorus is actually an element that we see in modern feathers. So here we are, a zoomed in area. You can see some of the lineations here a bit better, hopefully, and the same on the other side. So that was a really stunning result, and that was published back in 2010 and really showed what the power of the synchrotron could do. Now, it wasn't just phosphorus that we were looking at. We were looking at different elements all at the same time too. And I mentioned earlier about different elements coming from different places, and we want to be able to tell the difference. Now, here's the element manganese, which is very common in rocks, and actually very common in fluids that move around in rocks. And they actually form very distinctive precipitate or crystalline structures. And we see that on the bones of the Archaeopteryx here. And they make these like little pretty fern patterns. Now, if we had just taken the X-ray beam and plonked it on those areas that are in white there, we would have seen a manganese peak, and we may have interpreted that as belonging to Archaeopteryx, because manganese is also an important element inside organisms as well, not only in geochemical fluids. But because we can image it on this scale, we can see the characteristic patterns that make up this inorganic process and interpret that as not being associated with the animal. Not only that, we have curatorial artifacts. So more recent things where people have come along and tried to pretty up specimens, and you can actually see here where we have modern filler filling in holes of the bones. And then finally, this is a favourite of mine, in chlorine we can actually see fingerprints around the outside of the specimen where our sweaty paleontologists have been manhandling this specimen. And this is kind of, while funny, but it's also important because clearly we have contamination there. So if somebody was to come along and do some organic analyses and choose that area, it would very likely be contaminated. So very useful in a screening tool sense as well. So now hi kitty, hello. So now we move on to colourful chemistry and investigating how we can detect colours, like on my pretty little kitty here, in the fossil record. And so we move on to our next key publication using the synchrotron X-rays, and where we first kind of get the idea that we may have elements present in fossils that can tell us about specific biological processes, in this case, colour. So, we actually, this was a surprise result to us as well. This was another beautiful fossil that we were able to get access to and scan. Again, kind of rare, seeing lots of, this is a bird from China, a bit later than Archaeopteryx, now in the Cretaceous period, about 30 million years later. And again, an ideal candidate for the synchrotron because it's precious, a little bit rare, very delicate, and because it preserved beautifully preserved feathers all around the outside that we can see here in this kind of dark black carbon area. And a lot of people thought that this exceptional preservation kind of only extended to the microscopic level at most. This isn't quite one of those, but this is what at the time was considered one of the first true birds, in that it had a beak with no teeth and made out of keratin, like the fingernail material that we have. So we'll talk about keratin a bit later as well, so keep that in mind. So we scanned it with the synchrotron. On the right here is a false colour image, so higher intensity of these colours means there's more of it. And this is actually kind of just to represent the distribution, doesn't really represent true levels. But the thing here is that zinc is represented in green, and that's kind of there to show the background level or background of the rock that it's encased in. Blue is where the calcium is, and again, like we saw on the Archaeopteryx before with the phosphorus, calcium is concentrated within the bones. Not surprising, because bones are calcium phosphate, as I said, so no surprise there. But what was a real surprise was to see copper coloured here in red. Now, this isn't the colours that the synchrotron generates, these are colours that we make up afterwards to help us see the difference between the elements. a copper X-ray is not really red and a zinc X-ray is not really green. These are just colors that we use to try and illustrate the distributions in elements. So this result that we see in copper being highly concentrated to the feathers was a bit of a surprise. And so we wanted to understand where that copper may have come from. Now, as scientists, we often study the present to understand the past, and that's particularly true of paleontology. So what we decided to do was dig into the literature and see if there's any reason for copper to be in feathers. We then looked to modern day organisms and we looked at some feathers. Here's a couple here, but draw your attention to the main one, which is panel E here, which I believe is blue jay feather. And we like this because it was darkly pigmented and then had a white tip in a very sharp transition. And what was really cool is that that transition between pigmented and unpigmented was reflected in the copper map. So that kind of gave us a first indication that the copper that we see in our fossil might be related to pigment distribution. So we dug into the literature as well after finding and doing this imaging, getting this imaging data, and we found that indeed copper is present in feathers. And it's usually present in feathers because of the presence of a certain type of pigment called melanin. And melanin is actually pretty ubiquitous in life. It's the same pigment that pigments mine and your hair. Skin is the reason why you tan. And it's present because the melanin molecule likes to stick to metals, the atoms of metals such as copper, zinc, and calcium. And we'll get more into that later. And actually a lot of studies on melanin look at squid ink, because squid ink is a particular type of melanin called eumelanin, and we'll get onto that in a second as well. So we decided to look at a fossil and a modern squid, and we could actually see high concentrations of copper in their ink sac. So we started to formulate an idea that the presence of copper may indicate the presence of a particular type of melanin pigment called eumelanin. So we went the next step further because what we wanted to do is we wanted to get a bit more confident as to where this copper came from, because it's quite possible that the copper in the fossil of the bird itself could have been sucked up from the outside while the animal was degrading. So, or it could have been brought in by some other secondary process. So we did the absorption spectroscopy on the copper that I explained earlier. Now, what was really cool about the results from that is that we found that the copper in the fossil was actually present as an organic type structure, that is, a copper atom surrounded by oxygens or nitrogens. And so we wanted to know, well, does this copper kind of look like how it would have looked in the melanin molecule? So we reached out to a colleague, and they supplied us with their theoretical computational model for a melanin molecule. So this is represented by all these atomic balls around the outside here. And what was really cool is that the structure of our copper in our fossil fitted in the middle of our modern melanin computational model like a puzzle piece. So this was another really strong piece of evidence, to us anyway, that the copper we were seeing in the feathers of this 120 million year old bird actually came originally from a pigment molecule, eumelanin. And in that sense, that the copper image actually represented the distribution of that pigment in the organism when it was alive. And so we postulated this reconstruction of the dark eumelanin pigment. We thought it would be present where we saw the highest intensities of copper, and not present where we saw low intensities of copper, in particular out here on the very end feathers of the wings, which you could see clearly in the original fossil down here, but is not present in copper over there. And so we also believe that, I mentioned in the introduction that colours that we see on ancient organisms are completely made up. There's not much direct scientific evidence for that. So this was, we believed, one of the first times that a pigment reconstruction had been made based on direct scientific data, not only that from covering a whole organism instead of a few spots and being extrapolated out. And this was published in Science, one of the top scientific journals, back in 2012. So that was our really cool second huge result. And that spawned actually my postdoc and another 3 years of funded research to specifically look for pigment in the fossil record. I don't have time to go into all the studies today, but I'll take the key ones out of here. And so that led us onto studying pigments in a lot more detail, and particularly melanin. Now, why look at melanin in particular? There are actually lots of different pigments out there that make lots of different colours. So, for example, melanin, which I'll get into in a minute, is responsible for a couple of different hues. But then there's also things like carotenoids, which are present in things like that create bright blues, reds, pinks, things like that, and particularly those, you'd be familiar with those in flamingos. But in my cat here, it's likely that she's mostly got using melanin for her pigment. So, and the other key thing about melanin too is that actually melanin is the only pigment that really associates with metals, metal atoms in particular, as opposed to the others, which are what we would say are purely organic compounds. So really melanin is pretty conducive to being studied at the synchrotron because it has a metal element component such as this, which the synchrotron's able to detect. So what is melanin? Well, melanin is actually kind of hard to characterize. It's a very messy molecule made up of lots of subsections. But as I said, there's two forms of eumelanin. Two forms of melanin. Eumelanin, which part of that structure is illustrated on the right here. This is a kind of a typical organic-y looking molecule of carbon rings with oxygens and hydrogens scattered around them and nitrogens. And so eumelanin, on the left there, is mainly those elements I just mentioned and responsible for sort of dark brown, black type colours. And the other type of melanin is what's called pheomelanin. And pheomelanin is responsible for the reddish blonde hues that we see in people's blonde hair and red-headed people in particular. Is very rich in pheomelanin. Now, we were looking at trying to understand which elements are associated with which type of melanin, so we could get an idea, because often when melanin is present it tends to dominate a pigment of a tissue. And as we saw in C. sanctus, it seemed that like copper had a particularly high affinity for eumelanin. Eumelanin has lots of these kind of open-ended parts of the molecule which are really good to sticking and grabbing up different elements. And that actually makes, and same with the pheomelanin too, actually, with these end members, or these ligands sticking out the side. That makes it a very versatile molecule because, as I said, it's something that it's actually pigment that's present when we tan. We create more melanin as we tan, and that's because it's a UV protectant. So, and then not only that, it's present as a pigment in our hair, our eyes, skin, whatever. So, for animals anyway, it's a big part in how they produce color patterns in their external tissues, being used in either mating rituals or for camouflage, for example. So from a fossil paleontology point of view, being able to identify these elements and map their distribution in fossils is kind of important and interesting. So we went out and tackled a couple of different things. Now, the main thing to pick out between these two molecules here is that there's essentially not much difference in their overall structure. I mean, they look different shapes, but that's not something we can tell with the synchrotron. The results we were able to pick here, and we'll talk about later, is the fact that there's sulfur present in pheomelanin too, and we'll get it when there's no sulfur in eumelanin, and we'll get onto that a bit later when we look at modern feathers. So here's the two sulfur atoms here in the structure, and we'll get onto that a bit later. So I mentioned earlier, we're back with Archaeopteryx now, and we actually looked at the very first Archaeopteryx fossil, which you think, well, that's weird, that doesn't look anything like the previous fossil. And you'd be right, because the first Archaeopteryx fossil was actually this single feather. And importantly, when this was discovered, it pushed back in the 1800s, this was actually pushed the origin of birds back into the Jurassic period, whereas previously people thought they were after the dinosaurs. So pretty important fossil there, again, only one of them in the world, and it's called the holotype, which is basically, for any species, there should be a holotype specimen of which all other fossils are compared to. So extremely precious, but because of the non-destructive nature of the synchrotron, we were able to take a look at its chemistry. Here it is being scanned at the synchrotron back in 2012 or 2013. And we saw pretty similar results to those in the fossil bird, the Confuciusornis sanctus, where we saw copper and nickel present, elements known to be associated with melanin. And we also saw the presence of sulfur that we believed was coming from the original sulfur present in the protein that feathers are made out of, keratin. And so we saw more, so along with other data we collected, we believe that we could create this pigment reconstruction of the feather, showing a dark leading edge of the feather and a pale following edge. Now, the last sample we're going to talk about after this modern feathers, which is the fossil mouse, was when we started to get an inkling that we could try and identify pheomelanin in the fossil record and try and differentiate between the two pigments. However, we didn't have enough data to really justify our conclusions in that paper I'm going to talk about on a fossil mouse. So we decided we needed to take a step back and collect more data on modern melanin in order to understand what the signals coming out of the synchrotron would be for modern tissues. And so we decided to study melanin in a range of modern birds. So we took a look at feathers from 4 birds of prey. All of these birds were in rescue sanctuaries or rehabilitation centres. So we didn't go out plucking feathers off of wild birds. These all molted naturally off of these birds. And so what we have here on the left is a Harris hawk. And next to that we have a kestrel, a barn owl, and a red-tailed hawk. And we picked these guys, one, because they're relatively common birds of prey, but they also had feathers with a variety of, visibly anyway, differently melanized feathers, ranging from dark black all the way to a reddish gingery brown here in the barn owl. And not only that, seeing those different pigments in a single feather. So we wanted to get rid of some ambiguity of seeing feathers from different animals and different parts of the bird and literally go down to one feather. So that's what we did. We looked at single feathers. Here are the optical images of the areas of those feathers that we scanned. So you can see nice clear differences in pigmentation there. But we wanted to confirm what melanin was in there. And in fact, did they even have melanin in there? So we sent samples off to some colleagues in Japan who developed a technique for quantifying melanin. And indeed, we got confirmation that the different parts of the feathers with different levels of what to us looks like different pigment contain different levels of melanin. In particular, the Harris hawk there, you can see, has a lot of eumelanin, the dark black melanin in its dark area, and a little bit of pheomelanin. Now that's okay because most animals have a little bit of mix of the two, even in what appears to be particularly black or particularly red. The kestrel next to it, great comparison because we have a dark black stripe with a dark red area completely next to it, and we saw the right thing. We saw that the black stripe has a lot of eumelanin, a bit of pheomelanin. The red area has a bit of eumelanin and a lot of pheomelanin. The barn owl, which seems to be much less strongly pigmented, had a lot less melanin overall, but again, a similar sort of ratios as we'd expect. And then finally, the Harris hawk here, which was a very deep red, mostly pheomelanin with a little bit of eumelanin. So we confirmed the presence of melanin in these feathers. So we scanned them at the synchrotron. Here they are being scanned in the beam, and here are some of the resulting images. And so we collected a lot of different elements, but these are the key elements that are known, or were known in the scientific literature, to be associated with melanin: calcium, zinc, and copper, with the optical down the right-hand side. And so what you can see, hopefully, is that and what's pretty obvious to us anyway, is that these elements are the presence of these elements in the feathers are strongly controlled by the presence of the melanin pigment. If they weren't, we would see different patterns in the elements compared to what we see in the visible, but actually we don't see that. And especially in the Harris hawk, it's a beautiful set of images here that we can see when the melanin concentration drops off into the white. We get huge drops off in the element concentrations too. We can also see the stripes in the kestrel. And interestingly in that's a little different. We don't see that strong copper signal that we saw before, but what we do see is the presence of calcium enriched in the dark stripes, as we see it enriched in the black area of the Harris hawk. And then we actually see that there's more zinc in the red areas of the kestrel compared to its dark stripes. And this actually matched what we saw in the literature too, that pheomelanin has a stronger affinity for zinc than eumelanin does. So this kind of made a little bit of sense here. Here are the other two feathers following a very similar sort of pattern. Zinc associated with the red and calcium associated with the dark. And in fact, it's only really when things are really strongly pigmented, like the Harris hawk, that we tend to see copper concentrations in detectable amounts. So, more wiggly lines, don't worry. But the important thing here is that we did work on the zinc work, because we saw a difference in the zinc distributions in these feathers, and we also looked at sulfur, because I mentioned earlier that pheomelanin has sulfur in it and could be a defining characteristic here. So looking at the zinc spectra first, again these wiggly lines, the main thing to look out for is that the Harris hawk here in black has this peak here, and it's quite a nice symmetrical peak down here. This kind of represents zinc surrounded by oxygen and nitrogens. And the same here, look, as a natural eumelanin standard we created. But what we see here in the kestrel in particular is that we get a secondary bump here on this peak. And that's really interesting because that represents the presence of sulfur. So what we have there in the zinc absorption spectra is a difference where we see a decent contribution of zinc combined with sulfur, as well as combined with oxygen and nitrogen, but we don't see the sulfur at all in the very strongly eumelanized version. So that indicated to us again and strengthened the idea that zinc has a very strong affinity to pheomelanin. On the right here, we actually started looking at sulfur too, because I mentioned sulfur was important in the structure of pheomelanin. So what is the difference, or how does sulfur look in the pheomelanin molecule? Well, these two molecules here, benzothiazole, benzothiazine, both present in the pheomelanin molecule. And here is these compounds extracted, and we get very specific looking wiggles. And the other important wiggle that we have here is oxidized glutathione, otherwise known as a disulfide. Now this represents the base protein, the keratin that we have in our fingernails and in the feathers, because that's two sulfurs joined together, and that has a very distinct double peak here. So we're really interested in this double peak, this benzothiazole here, and this benzothiazine. So we looked at all the feathers using the sulfur absorption spectroscopy, and the key result here, particularly from the kestrel and the red-tailed hawk, is that we look at the white area, which is kind of essentially non-pigmented keratin protein, so it should look like that oxidized glutathione we saw before, the disulfide, and we see the characteristic double peak that we saw before. Next we looked at the dark eumelanized stripe and partly pheromelanized stripe of the kestrel, and we see again dominated by the protein of the feather, because that's what most of the sulfur in the feather is. But we get some slightly different bumps here as well. Maybe that's indicative of some pheomelanin that we can detect. But the really key result here is the slight difference in this double peak here, that the fact that there's enough presence of pheomelanin in the dark red area that the signal from this type of sulfur molecule is actually changing the shape of the spectra, and we see that as this peak being higher than this peak. So what we're actually able to show here is that when we looked at the sulfur, we saw a difference in the wiggly lines, and when we looked at the zinc, we saw a difference in the wiggly lines. Both important because it's the presence of the added sulfur from the pheomelanin molecule in the heavily red areas of the feather. So this was really cool. We had this data and we were armed with it. We thought we had a good way to conclusively or pretty strongly look at pheomelanin and be able to detect melanin in fossils. And so we move on to our final fossil, which was only published last year. This is a fossil mouse called Apodemus. Basically, it's an extinct species of a mouse like today's field mouse, and beautifully preserved sample. You can see it's pretty tiny, only 1 centimeter scale bar there, so only yay big. And this was found in Germany again, Willhausen, the location is called, which consisted of a very small, deep lake, which didn't have any oxygen at the bottom. So it was pretty conducive to preserving soft tissues in an exceptional way. And you can see that here, because we can almost see the individual hairs and of the fur surrounding this animal. And we had scanned this at the Synchrotron a few years before we even undertook the feather study, but now that we were armed with that feather melanin data, we were able to tackle this mouse again. And in fact, here's the false color image, and again, we see that phosphorus here, which is colored blue, concentrated to the bones, as we saw, it makes sense before. The red represents an organic sulfur. Unfortunately, I didn't have time to go into how we map organic sulfurs specifically. But that shows up in the fur beautifully. And actually, just going back to the phosphorus, you can even see its little earlobes, which makes sense because we've got phosphorus in the collagen of our ears. And then finally, this area is dominated by yellow, but it's actually a mix of the presence of zinc, which is colored in green, and the organic sulfur. So we actually have a mix of zinc and sulfur in these areas, kind of in the fur and skin areas like this. And again, hopefully I've emphasized that the stereotype of paleontology being a science dominated by people in tweed jacket and elbow patches, or being Ross from Friends, isn't true. We are scientists like all others, and using state-of-the-art techniques to try and understand more about the ancient world. I've talked a lot today. I've talked about synchrotrons, X-rays, pigments, Archaeopteryx, sea sanctus, many different things. And hopefully you've been able to take something away from that today. And how we've brought together two worlds of particle accelerators and paleontology to understand more about ancient life, and how we've gone from looking at the X-rays generated from a particle accelerator to help us identify the chemistry, the elements present within a fossil, and how those elements might be associated with specific biochemical properties of an animal, in this case pigments. Now, we've done a lot of other research using the synchrotron, not just looking at colours, and we've studied lots of other different types of organisms, such as plants, bones, manatees, dinosaurs, all sorts of things, and we may get around to talking about those at the Q&A on the 2nd, so please join us then, and thank you very much for that. So before we sign off, I just want to acknowledge a few of the people involved in this research. There are loads more than what's represented here, but I just wanted to point out that this research and the results that I've described today are only possible due to the combined efforts and expertise of people from a variety of different fields. Because we've talked about particle accelerators, X-rays, biology, biochemistry, paleontology, and it's only really with the combination of experts from each of these fields that we're able to come up with the conclusions that we do. So just to point out some of the key people in the research group, that's Phil Manning, who's the lead paleontologist from the University of Manchester in the UK. Roy Regalius, the lead geochemist, and Uwe Bergman, the physicist in our group from SLAC National Accelerator Laboratory. On a personal note, I just want to do a big shout out to my mum and dad, Malcolm and Teresa, who supported me throughout the years on my desire to become a paleontologist, supported me both emotionally and financially, and I wouldn't be where I am today without their love and support. So just really want to thank them and acknowledge their contribution.
One dinosaur hanging up, Mummy! One dinosaur hanging up!
Oh, yes.
Yes, baby!
Let you show me.